When I create problems for a physics class, I think of them as fundamental problems, good problems, cool problems, and super cool problems. Now, in this class, I'm trying to give you mostly just fundamental problems and good problems. Fundamental problems are problems that you just take the formulas, you apply them in a straightforward way, and you should be able to get the answer. And so it's just really a matter of making sure you can identify what formula and what everything means in using it. Cool problems, or good problems, pardon me, good problems are a little bit more complex than that. And in a class like this, I expect maybe a third of the students to get the good problems without any help, which is why you guys have a video for every single problem. Then I try and avoid cool problems in all my classes because cool problems, quite frankly, uh, there's going to be maybe one or two students can solve a cool problem in a regular class. If I gave a cool problem to this class, maybe one or two. Super cool problems, are ones that I have to spend some time thinking about and reaching to understand. And so even in one of my more advanced classes, if I gave a super cool problem, I would expect the students to ask for help. This problem is a magnificent problem. I love this problem. And I love this problem for some things it illustrates. And it took me a while to kind of get my head wrapped around what was going on exactly with this problem, even though it is deceptively simple. Here you are. You have you have a table, and I'm going to label some things, and we're going to do videos maybe in parts here because this is going to get kind of long. Um, you have this table, and I'm going to label the legs 1, 2, 3, 4. And one of the problems that we have with this with tables, and you're familiar with it, that gets illustrated in this problem to some extent, is that you know you don't, and if you've ever eaten at Hey Joe's, you know this for sure. You don't have to have all four legs on the table on the floor for the table to just sit there, right? And you have this problem in the cafeteria, you have this problem at Hey Joe's, you have this problem anywhere you go, and you sit down. Tables do A four-legged table does not have to have all four legs on the floor, which is one of the things I was running up against with this problem. So this is how we're going to think about this problem. All right, we've got, and I'm going to call these force 1, force 2, force 3, and force 4 for the forces provided by each of the four legs. Now this table is square, it has a length, and we're going to stick a book on it somewhere. And I don't really care where the book is. We're going to stick a book on it somewhere, or a blob of nachos or something. Okay, really heavy nachos, right? I mean, when's the last time you ordered 20 kilos of nachos? Um, okay, so here we go. Um, if you're going to eat 20 kilos of nachos, you need several liters of something else to go with it. Um, so here we are. We've got our four forces. And this is a two-dimensional, right? It's a 2D statics problem involving forces and torques. Now, I'm going to take a simplifying step in terms of all the algebra, which is let's just accept that the weight of the table and what the book is doing can be treated as two different things because the result is the sum of the two. And the weight of the table, um, call it the weight of the table, which is mg, right? Mass of the table times gravity. So whatever this mass up here is, right? So 14.5 kilos times 9.8, you get the weight of the table. And we're going to assume the weight of the table is all symmetric. And so the force from each leg due to the table is just a fourth, right? So each leg, um, the force from each leg due to the weight of the table is just a fourth of that. Okay. And so now we're looking at, now that we've taken that out, because we can do that. We can add up the effect of everything separately. Um, Now that we've taken that out and we're looking at just the table, I mean just the weight on the table, and the table has no mass at this point. We're just looking at how can four forces at these 4 points support a mass that's at some spot on this tabletop, right? And so we'll start working through those formulas in the next video, but here we have F1, and we have F2, right? We have F4 in the back and F3 up front. And so we're going to talk about the torques. So if you look at this table from this side, and you look at it as if it were just a simple two-dimensional object instead of a three-dimensional object, this force from this end we'll call F12 to represent the sum of those. And this force from this end we'll call F34. I do a great 3. Let me just add to it. There we go. We've got the weight here at some position X, and we've got the length between the legs L. And I say assume that the legs push all the way out to the corners, although I didn't draw it that way. And so if we're going to look at the torques here, let's choose our pivot point over here. Well, since our pivot point's over here, F12 doesn't provide any torque. It's just X times, I'll call FB or FW, FB, we'll call it FB. FB, the force of this blob, and so X times the force of the blob, its weight, right, mg, equals, and this is just going to be L times F34. And we'll type all this out later. The other way to look at this same torque is this distance from here to here is L minus X. And so if I put my pivot point over here, what I end up with is L minus X FB. Oop, yes, I write so well. Is, and then again, that distance is L F12. So we've got two equations so far that are dependent on each other. They're not independent equations because it's the same plane. F34 is, I mean, F34 is X over L FB, and F12 is L minus X over L FB. And if we look at the other end, if we look at it from the other end, that would be from this end, and we're looking back at in the Y direction, we get something very similar. We get Y onto FB is L onto F24, and we get L minus Y FB is L F13. And again, these are not independent, but we're going to, and that's just looking at the same scenario where all I've done is looked at it from this side instead of from the front, and come up with the torque equations. And the other equation we know in all of this is the weight of the blob has to be equal to F1 plus F2 plus F3 plus F4. And for those of you who know your linear algebra, um, yes, I know, that's a joke. For those of you that know your linear algebra, we now have 3 equations but 4 unknowns. And so this system is not going to be something we can solve in a straightforward way. Okay, so that's it for part 1 of this video. All right, you do the torques, you do the sum of the forces. This problem is harder than that because this doesn't get you to a solution right away. We're going to pop in another video, and we're going to start working through with me typing out the solution, getting to what we can do with this problem and how can we get down to an answer that we can calculate. All right, see you in part 2.